Lightweighting electric automotive vehicles of the future with advanced composites is an approach under development by the Ford Motor Company. As the poster child project within the Institute for Advanced Composites Manufacturing Innovation, Purdue-CMSC worked with Ford and Dow Automotive to develop a liftGate for a future SUV from carbon fiber composites. The goal of the project was to reduce weight while producing a structural part in less than 3 minutes. Dow Automotive provided rapid cure epoxy systems, and Purdue guided the development of a molding compound with a balance of high flow characteristics with the strength of aluminum. Flow simulation at CMSC succeeded in modeling anisotropy and viscosity of these new material systems and in optimizing charge patterns within large compression presses typical in these systems. The first liftgate prototypes were molded in Continental Structural Plastics in Huntington, Indiana, while CMSC's partner at the IACME scale-up facility in Detroit, Michigan, provided multiple molding study results. The project made Dow Automotive Systems a PACE Award finalist in 2018 for processing speed and recyclability needed to utilize carbon fiber composites in mass production. The manufacture of carbon fiber composites with compression molding requires the machining of molds, typically in steel, of identical geometry as the desired part, and cost of these molds can be prohibitive when multiple part geometries must be investigated to achieve optimum geometries. The virtual twin concept can predict the optimum mold geometry and thereby reduce the cost significantly. A second development presented earlier is composites additive manufacturing. This process allows printing of the molds to achieve prototype geometries at significantly lower cost and mold production time. The major cost, however, in developing new composite products or materials is in the expense of testing thousands of material samples to determine design allowables. Virtual allowables offer the opportunity to provide these data through digital twins of accepted test methods administered by the standards organizations like ASTM, ASE, and others. The digital twin reflects the variability of the material microstructure on its properties and produces statistical property data that can be merged with real data to yield design allowables at half the cost. The flow of carbon fiber filled thermoplastics in the melt state is highly anisotropic, so that the flow directions and orientation state of the fiber suspended in the polymer can change with flow direction. The Dassault Systems Smooth Particle Hydrodynamics option within Abacus and 3D Experience provided the platform for the virtual twin of this complex flow in these molding simulations. The molding of a typical mechanical component for aerospace application shows that each platelet within the material can be followed throughout the flow process, and the resulting orientation state, when compared to X-ray computer-aided tomography scans, shows very close agreement between scan and the virtual twin, and thereby validation of the simulation. The thrustReverser blocker door for a gas turbine jet engine is a complex structure that slows the commercial aircraft on landing by diverting the thrust of the engine laterally. The virtual twin for the manufacture and performance of the blocker door illustrates the significant advantage simulation provides in transforming this product from the conventional design to one in advanced composites, and thereby achieve weight savings and reduce costs. Not only can the design of the blocker door be developed as a digital twin, but the development of the prototype molds as illustrated by a joint project with Thermwood. In this project, the print direction of vertical versus horizontal was considered in the digital twin. Next, the transfer of heat into the mold was examined to determine the uniformity of temperature inside the mold when heated by the platens of the press. On determining from the digital twin that the temperature distribution was unacceptable via the digital twin, the simulation of cartridge heaters inserted into the mold led to the final and correct molding conditions. The final blocker door prototype was successfully molded in an additively manufactured composite mold. This success was both a breakthrough in technology and a demonstration of the power of the digital twin in new product development.